Hello everybody, this is Rudra Pradhan here. Welcome to BMD lecture series. Today we will continue with prescriptive analytics, and that too coverage is on nonlinear programming. So, we have discussed couple of business problems dealing with linear programming, and under linear programming we have discussed several cases, several instances, and we find there are lots of flexibility we have in the prescriptive analytics to solve the business problems depending upon the particular situation, or the depending upon the particular case, or with respect to number of constraints and the kind of requirement, the kind of conditions. So, that means technically prescriptive analytics having lots of kind of advantages through which we can actually solve some of the business problems depending upon the type of requirement and the kind of business requirement. So, now connecting to the previous discussions that is related to linear programming. So, today we strictly highlighting the issue with respect to nonlinear programming. So, that means technically whether we like to apply linear model or nonlinear models, that exclusively depends upon the type of data, the kind of structure, the kind of business problems. Usually we cannot actually build a linear models by default. So, having the clue or getting the clue from the data set or the kind of business problems, we can actually develop the model, and then we look for the optimality, that is the values of the decision variables, and that too for the prescriptive analytics to solve the business problems and come with a kind of management decision as per the particular requirement. So, that means that is how in the previous couple of lectures, starting with descriptive analytics, then the inferential analytics, predictive analytics. So, every times the typical suggestion is that, so we have to go through very in depth the data visualizations, the understanding of the problems, the kind of dynamics of the problems. Then on the basis of data data availability or informations, then the kind of business theory or the kind of issues and the kind of challenges. Then we try to transfer the particular model into a model, and that model since it is a kind of data transformation to the model or problem to model. So, obviously we cannot just transfer the typical problems or issues to kind of linear model. So, the transformation of information and data to model, whether it is a linear one or nonlinear one, depends upon the situation, and data itself will read the things, and accordingly we can actually develop the model. So, now after knowing all these details from the data visualization, the kind of problem requirement and the kind of dynamics of the problem. So, assuming that the model is a kind of nonlinear one, then we will look for the kind of solution, that to optimal solutions, and where we look for the values of the decision variable through which you can address the business problem more effectively, and then come with a kind of management decision as per the particular management requirement. So, so we have already discussed like in the case of predictive analytics. So, having the data, having the problems, we can first start with a linear kind of model, then go for the estimation, go for the kind of optimizations, and look for the solutions. And in fact, there are lots of test procedures or diagnostics or robustness checks through which you can give the kind of or the you can find out the kind of clues or the kind of inference, whether the typical model, that is the linear model, is perfect one for the business predictions or business kind of forecastings. If not, then we have the option to change the particular structure, and again re-estimate, re-optimize, then look for the final optimal solutions which can be very effective as per the problem requirement and the kind of business requirement, and then we can come with a kind of effective management decision. So, now with this basic background, so we like to highlight what is the concept of nonlinear programming and how it is actually different to linear programming, and how is the kind of solution, that is the optimality and the values of decision variable through which you can address the business problem more accurately. So, if you like to see the like to analyze the difference between the linear programming and nonlinear programming. So, it is not highly different. So, they are more or less in the similar kind of basket, but the difference is just the kind of functionality only. So, so far as structure is concerned, it is more or less same, because our optima means our final or the immediate requirement is the optimal solutions, and that too values of the decision variable through which you can actually address the business problem as per the typical management requirement. So, that is why since the that is why it is not highly different. So, obviously, the concentration is on typical objective function, that is how to address the business problem. So, like linear programming, here most of the instances nonlinear programming can be also having objective functions, constants and the conditions, and look for the optimal solutions and the values of the decision variables. So, that means the problems which you are discussing in the prescriptive analytics and the tools which you are using, various tools which you are using, mostly the kind of optimization tools. So, now I will give you little bit background about the details of the optimization structures, then we will come with a kind of nonlinearity structures, and then we will connect some of the problems, and then how we can actually obtain the optimality or optimum solution through which you can the same nonlinear programming in the similar way can analyze the business problem more effectively like linear programming. So, obviously, the issue is like this. The kind of structure is so we have the kind of structure here. So, this is a kind of optimization. So, that means technically the optimization tool is typically two types. So, it is the kind of linear optimizations, and the kind of nonlinear optimization. So, here in the case of linear optimizations, we have objective functions and we have constraints. Okay. So, in the nonlinear programming, so that is how the kind of we have again objective functions and then the kind of constraints. So, it depends upon case to case. For instance, objective functions can be 1 and can be multiple 1, that is what multi objective structures, and constraints can be 1, can be 2 and can be more than 2, right. So, this can be the kind of structuring, and here also the kind of structure is we have objective functions, ones, and it can have also more than two objective functions, and then constants, it can also have one constants and it can have also multiple constants, right. So, this is how the typical structure through which you can actually address the business problem. So, now in the case of constraints, so we can have actually in all the kind of situation, we may have this structure like equality constraints and then non-equality constraints, non-equality constraints, right. So, here also in the constraint sides we have equality options and we have non-equality options. So, that means this is the typical flow chart under the optimization. So, in this in this context we are looking for the kind of optimal solution, and then then we can address the business problem as per the particular requirement. So, that means taking the clue from the optimization structure, which can be can be divided into two different ways. So, the linear one and the nonlinear ones, and in the linear case we have objective function, we have a constraints, and again in the nonlinear programming problem we have also objective function and we have the constraints. So, the objective function can be a single one or multiple one, and constraints can be single one or multiple one. Again constraints can have equality structure and inequality structure, and these are all equally true both for linear programming problem and nonlinear programming problem. So, this particular lecture is specifically or exclusively concentrate on nonlinear programming problem, where we must have actually a particular objective functions and then constraints. So, sometimes we have a problems having objective functions and there may be constraints and there may not be constraints. So, that means technically. So, now we can again formulate the nonlinear programming problems corresponding to the typical optimization structure. So, the nonlinear programming structure will be like this. So, one with objective functions without any constraints, So, that means non constant optimizations. Then here objective function with constraints, right, with the constraints. So, this is what actually the kind of division. So, objective function without any constraints and objective function with the constraints. So, this is what it is called as a constant optimization problem. So, in this case we have only objective functions, and the objective functions can be of two types, single objective functions and multiple objective functions, and that too with single variables and the kind of multivariable case, right, multivariable case. Similarly, here we have objective functions and we have constraints, and then the objective functions may be with respect to since it is a constant. So, it will start with 2 variables and more than 2 variables, and then constraints which can have actually 1 constraints or more than 2 constraints, and again some are equality type and some are inequality type. So, why these classifications are required? Because we have actually different kind of structure through which you can actually apply the linear and nonlinear programming problems. Generally, we use calculus based kind of solution through which you can address the business model and the business problem as per the particular requirement. So, we have a different kind of techniques, and depending upon the kind of problem, depending upon the kind of structure, we look for the solutions and then address the business problem as per the particular requirement. So, that means technically starting with the nonlinearity structure. So, without constraints and then with constraints. So, let us see the particular structure where the problem is of nonlinear programming, and where we have only objective function and no constraints. Then again we can analyze the situation where we have objective function with constraints, right. So, that means technically we have 2 different structure altogether in the case of nonlinear programming, and then we like to see how the optimality structure in both the cases and how they are different to each other to address the business problems. Obviously, we can start with a objective function and then we look for the optimality. Then over the times we will find there are lots of constraints which can affect the objective function or business objective. So, as a result, so the unconstrained optimization can move into the constant optimization and then look for the optimal solutions and the values of the decision variable through which you can address the business problem more effectively. So, that means the in the case of nonlinear programming typically. So, that is objective functions without constraints. So, that means it can be have a single objective function, means with that is with respect to single variable case, and then we have actually multivariate case, okay, variables case, right, the single variable case and multivariable case. So, it depends upon a particular business scenario. Of course, in the big business and the dynamics of business, we will find a business problem which can be addressed within a multivariate environment. And as a business problem with a single variables is you may find rare in the real life scenario, but still we like to know how is the typical structure, and then we will move into the multivariate case where most of the business problems can be addressed there, and then look for the optimal solutions as per the particular management requirement. So, now in the case of single variable case, let us assume that z equal to objective function which is nothing but f of x. Okay. So, that means it is a objective function with a single variables. Now, we look for optimal solution. So, in the case of nonlinear programming, so we like to go for again the optimality and the values of the decision variables at the optimal stage through which you can address the business problem. For instance, let us say this is a kind of profit functions, then we like to know what is the maximum level of output through which the business firm can reach optimum profit. So, that is how simple structure can designs and then look for the optimal solution. So, so the typical structure is like this. So, that means here we look for the optimality, and in the case of optimality, that too in the nonlinear programming problem. So, we wish to follow the calculus based structure through which you can look for the optimal solution and values of the decision variables. So, that means technically so there are two different structure altogether, and in the case of calculus based mechanisms. So, there is a first order necessary condition and second order sufficient condition, and that too it depends upon the kind of types of objective function, whether it is a maximization type or minimization type, but the typical structure is more or less same. For instance, so when I am writing z equal to f x, so this is not actually clear cut signal what to do exactly. So, now we have to specify first the objective functions. Let us start with maximization of z, then it is a kind of meaningful specification. So, and as a result you can actually apply a particular technique through which you can look for the solution. So, that means so there are two different structure, first order necessary condition and second order sufficient condition. So, far as a calculus based optimality is concerned, and this is the kind of structure which we usually apply in the case of nonlinear programming problems, and that to nonlinear programming optimization. And in this case that is with respect to objective functions, that is the maximization of z, and that to f of x, that is the case of single variable. Then here the first order necessary condition will be like this, f dash x should be equal to 0. So, that means it is nothing but actually dz by dx equal to 0, and then in the second order sufficient condition will be f double dash x should be less than equal to 0. So, that is with respect to maximization. So, and in this case it is d square by z by dx squares less than equal to 0. So, this is how the one variable case, and so having the, that means technically what we like to do here, like predictive analytics. So, we have a data corresponding to a particular business problems. So, using the data you transfer the data into a model, and then you check whether it is coming in the linear structure and nonlinear structures. After lots of diagnostic check and robustness checks, we will have a models which is actually nonlinear type. Then we can apply this calculus based methods through which actually we look for optimal solution, and then the values of the decision variable through which you can address the business problem. So, this is how the typical structure. So, once you get the kind of structure the objective functions, and that to the requirement is the maximization type. So, this is the structure which you can apply, then look for the optimal solution and the values of the decision variable. So, now in the case of minimization, the typical structure is more or less same, that is the case of single variable. So, just you have to change the objective function structure maximization to minimization. So, whether it is a maximization type or minimization type, the first order necessary condition is more or less same, that is the first differential should be equal to 0, that is dz by dx equal to 0, and the second order condition will be different, and in the case of maximization the second order differentiation will be less than to 0, while in the case of minimization it will be greater than to 0. So, that means, if corresponding to objective functions, if it is a maximization type, then f dash x equal to 0 and f double dash x should be less than equal to 0, and in the case of minimizations, same f dash x equal to 0, but f double dash x should be greater than to 0. So, this is how the typical case in the case of one variable case, and that too without any constraints. So, now let us see the situation in the case of multivariable case. So, if it is a multivariable case, then the objective function will be with respect to at least two variables. So, that means technically let us maximize z equal to f of x1 and x2, and then we look for the optimal solutions. We look for optimal solution, that means what should be the x1 value and what should be the x2 value through which the particular functions can be reached at the highest levels. Obviously, x1 is the kind of decision variables, may be with respect to profit, may be with respect to revenue. So, we like to optimize the revenue functions, and we like to optimize the profit functions, and in this case, so the typical structure is again same. So, we have a first order necessary conditions and we have a second order sufficient conditions. And in the case of first order necessary conditions, so we can have actually dz by dx1 equal to 0, and then dz by dx2 equal to 0. Okay. So, this is first order necessary condition. So, that means, so this is nothing but called as f1 and this is nothing but called as f2, and then and this is also same in the case of minimization of the objective functions, and in the case of second order sufficient condition. So, we have actually different kind of structure altogether. So, for that we can have a matrix, a Hessian determinant matrix. So, this can be f11 and f12, f21 and f22, that is the double derivative, that means second order differentials which you can actually apply. So, now the entire matrix should be like this. So, that means technically in the second order sufficient condition for multivariate case little bit complicated. So, in this case, so the requirement is for the maximization structure. So, f11 should be less than 0, f22 should be less than 0. So, that means this diagonal elements, and then the off diagonal elements and the kind of the kind of matrix combination, the entire matrix should be greater than to 0. So, this is how the typical requirement, and that is what the case of maximization of objective function, and in the case of minimization of the objective function, the typical process is more or less same, but the difference is actually with respect to the second order differential. So, in the case of minimization, minimization of objective function, so the second order objective function, that to the diagonal differentials will be greater than to 0, and then f22 also greater than to 0. So, rest of the things are more or less same, and that too with the case of multivariate situations. That means a particular objective function can be specified with respect to more number of variables. So, since we have actually different kind of business issues. So, obviously, the total revenue or total profit may be the sum of two or more than two different products. So, obviously, the typical objective function will be multivariate in nature. So, now having the multivariate in a kind of objective function. So, we look for the optimal solution, and using the calculus based methods. So, we can follow the typical structure like this. So, that means we have discussed the typical structure in the case of one variable case, two variable case, and that can be generalized for multivariate case. For instance, in the case of multivariate case, let us say z equal to f of x1, x2 and so on, let us say xk. So, then what should be the optimality structure with respect to multiple variables, and again that depends again with respect to objective function, type of objective function, whether it is a maximization type or minimization type. So, obviously, so the first order necessary conditions every time will be f 1 equal to 0, f 2 equal to 0, then continue f k equal to 0, and that too with respect to x 1, x 2 and x k. So, these are number of variables which can be in the particular business process, and the second order sufficient conditions as a two different structure. In the first structure is with respect to diagonal elements, that is f 1 1, f 2 2, f 3 3, then continue up to f k k, and that is with respect to x 1, x 2, x 3 and x k. And in the case of maximization, this should be less than 0, 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 and in the case of minimization, it should be greater than 0, it should be greater than 0, it should be greater than 0, and it should be greater than 0. And in the second order sufficient condition, this is the first issue, and in the second issue is the complete determinants. So, that is what let us assume that it is actually case of 3 variables, then f 1 1s, then f 1 2, f 1 3, or you can continue with up to f 1 k. So, that means technically this will be go up to f 1 k, and then f 2 1, f 2 2, f 2 3, and then this will continue with f 2 k, and again this will continue, this will continue, this will continue, then finally f k 1s, f k 2, f k 3, and it will continue up to f k k. So, that means technically we have two different structure here, the diagonal structure and the off diagonals and on diagonals. So, regarding the diagonal structure, which you have already specified here with the case of or with the requirement of maximization type and minimization type, and in the case of second structure with respect to sufficient conditions, second order sufficient condition, this matrix should be greater than equal to 0. So, this is how the kind of optimization principles with a objective function and that to have no constraints, and we have highlighted 3 different situations. In one situation we have a single variable, another case we have a 2 variables, and then we can extend it to multivariable case. So, that means depending upon the type of business problems which you like to analyze. So, we try to see what is the typical case. So, whether it is a 1 variable case or 2 variable case or multivariable case, then you transfer the particular problem and information to a models, and that too in a kind of a situation where the model is a kind of nonlinear in character. Of course, we cannot just arbitrarily design the particular nonlinear model. So, the data itself will give you the particular structure. So, once we get the particular structure, assuming that the particular structure is coming in the form of a nonlinear format, and that too whether it is 1 variable case, 2 variable case or multiple variable case. So, these are the procedure which you can follow, then look for the optimal solutions. So, that means the typical requirement of the nonlinear programming is that you must have a knowledge about the calculus, and then manually you can actually go for the solution like this, and otherwise it is very difficult to get the optimality depending upon the particular business requirement. Of course, we have a Excel solver where we can also without any manual calculation, we can just give the kind of instruction to the solver. So, solver will give you the optimal results and that to values of the decision variables depending upon the particular business problems or the kind of business conditions. So, now so these are the cases under objective functions without any constraints. So, that means we have discussed 3 different situations under nonlinear programming problems, and that too we have objective functions without any constraint. So, first case with the single variable, second case with the 2 variable, and third case with more than 2 variables, and every case we have no typical constraints to address the business problem. But in real life scenario or in the kind of dynamics of the business, we will find the particular business problems may have constraints, and then we look for the kind of optimal solution depending upon the particular business requirement. So, in this case again we will see the particular optimality structures and look for the optimal solution. So, that means the second part of the model is called as nonlinear programming problems with objective functions and constraints, right, constraints. So, this is how the typical case. So, in this case we have objective functions and we have a constraints, and obviously we can have a objective function, single objective or multi objective, or single variable case, multi variable case, and then we have a constraints, and the constraints can be of one constraints case and two constraints case, and then in the first instance we will have actually the type of constraints. So, one type of constant is called as equality signs or equality constraints, and then this inequality constraints like which you have already solved in the case of linear programming problem. So, now the typical nonlinear programming with constraints, that means constant typically it is a kind of constant optimization problem where we have objective function and constraints, and that to one variable case and multivariable case, and then with respect to constraints we have this scenario called as equality type of constraints and inequality type of constraints. So, depending upon the constraint structures, equality type or inequality type, we have two different mechanisms. So, the first mechanisms under the particular constant optimization problem, that to under the nonlinear programming format, is called as equality constant, and for that the standard method to look for the optimal solution is called as a Lagrangian method. So, that means this in this case we use actually a Lagrangian methods to solve the optimality and values of the decision variable, and if there is a kind of inequality type of constraints, we look for the kind of solutions, and that too we apply Kohn-Tucker conditions. So, Kohn-Tucker conditions mechanisms. Okay. So, mechanisms to solve the problem. So, so this is how the kind of game here in the case of constant optimization. So, we have objective functions, we have a constraints, and depending upon the number of constraints the typical structure will be the equality type of constraints and inequality type of constraints. Then in the case of if the particular problem is a type of equality type of constraint, then the standard mechanism which you can apply to have the optimal solution is called as Lagrangian multiplier methods, and then if the constraints are typically inequality type, then Kohn-Tucker condition or Kohn-Tucker mechanisms can be applied to look for the optimal solution and the values of the decision variable through which you can address the business problem. So, that means technically we like to know how is the typical structure in the case of Lagrangian mechanisms and in the case of Kohn-Tucker mechanisms. Let us see here. So, in the case of first case, so case 1 it is a objective functions with constraints, and that to equality type, and that to equality type. That means we have let us say y equal to function of x, and subject to there is a kind of constraints. The constraints will be let us say kind of say h of x, that is actually the kind of constraints type, which is actually nothing but equal to b, and because sometimes it is called as budget constraints, and depending upon objective function, if the objective function is a profit type, then the first end constant will be called as budget constraints, and then we look for the optimal solutions. So, the first end trick of this particular process is to have a single functions which can be actually obtained by clubbing the objective function and constraints, and the mechanism through which you can club the objective function and constraint is through multiplier, and that is through Lagrangian multiplier. That means technically having the objective function like this and the constant like this. So, the first and the requirement or first step of this particular process is to have this is actually f of x and then f of x then minus lambda lambda h of x. So, this is how the objective functions, and then again we like to look for the optimal solution. So, the typical difference is here actually you try to build a single functions which is the combination of the objective function and constant. So, now once we get the single function which is the cluster of objective function and constants, then the procedure to have the optimal solution by calculus based method is more or less same. So, like the case which we have already highlighted where we have no constant or at all. So, in this case the typical structure will be like this. So, again the first order necessary condition will be dz by dx equal to 0 and then dz by d lambda is equal to 0. So, this is the first and necessary condition, and of course, I am just putting dz by dx equal to 0, but it depends upon number of x. So, this x is a vector and it may be with respect to one variable, it may be with respect to two variables, it may be with respect to three variables. So, now having the kind of structure, so then you can extend, that means technically. So, dz by dx equal to 0 means it may be dz by dx1 equal to 0, dz by dx2 equal to 0 and so on. Again there may be situation that we have actually more than one constant. So, in that case so you can put lambda 1 h1 x, lambda 2 h2 x and so on. So, then again means accordingly. So, dz by d lambda 1 equal to 0, dz by d lambda 2 equal to 0. So, depending upon the particular requirement. So, that means corresponding to objective functions and with a single variable and that with multiple variables, we may have a single constants and we may have a multiple constant. So, having more number of variables and more number of constants. So, you will find the problem will be more complex in nature, and in that case we look for the optimal solutions, and then again so the first hand requirement is with respect to dz by dx equal to 0 and dz by d lambda equal to 0. Then we create a again Hessian determinants, and which can be with respect to 0 p and then this is the p transpose and q. So, the p is the kind of the first differential of the budget constant, and these are all called as second order matrix, which we have already discussed, like f11, f12, f2, f13 and so on. And so, your idea is actually to calculate the Hessian determinant and check how is the kind of structure. So, in the case of multivariate case, so the typical structure depends upon the sign of this Hessian determinants with respect to one variable, two variables, and with the order of the matrix with respect to 1 into 1, 2 into 2, 3 into 3. So, that means the value of the square matrix. So, it depends upon situation to situation. The nature of this particular Hessian matrix may have different options. It can follow a particular trend, increasing trend or decreasing trend, and ups and downs. So, this will give you the signal that how is the behavior of the objective functions, and that to address the business problem as per the particular requirement. So, that means typically the nonlinear programming problem structure is very complex, and the first hand complexity will start from the functional forms, which is actually nonlinear in character, and then again the complexity will be added into the process by integrating the constants, and again further complexity will start by adding one after another constants into the process. So, now this is the typical problem through which actually the kind of constant optimizations, and that too in the nonlinear problem programming we will address, and then we look for the optimal solution as per the particular business requirement. So, now corresponding to the case ones where we have objective functions and equality constants, and the standard method which you can apply is called as Lagrangian multiplier. So, the combination of the lambda which can actually club the kind of objective function to constant, that is how it is called as Lagrangian multiplier methods. And in the case 2, the typical difference is the constants are less than type situation. For instance, in the context of case 2. So, let us start with case 2 here, and this is objective functions, and where y equal to function of x, and then the constants will be h upon x is less than equal to b, or greater than equal to b. So, in that case, like the case of linear programming, where most of the problems which we have discussed is inequality type, and here this is a special case till now whatever we have discussed, where the constants are inequality type, and here we have objective functions, we have actually inequality constants, and the idea is just to club the objective function with the constants, inequality constants, and to come with a kind of final functions through which you can look for the optimal solution and to address the business problem. So, in this context what will you do, just club, and then again the same procedure we have to follow, but before clubbing, so we use actually slack and surplus variables. So, that means technically, so this instead of this one, so first and transformation is the the kind of constant side h x less than equal to b. So, that means technically it is nothing but h x plus s equal to b. So, this is what the kind of constants. So, now again, so when we like to add all these things, so then the standard equation will be h upon x plus s minus b equal to 0, then that will be just connected with lambda, and then look for the solution. So, then in the kind of optimality structures, earlier we have dz of dx equal to 0 depending upon the number of x, and then dz by d lambda equal to 0 depending upon the number of constants. If there are 2, then lambda 1 lambda 2, if it is 1, then simply lambda, and then since we have used actually slack variable or surplus variable the s type, then in this case one more requirement is dz by ds equal to 0. So, that means the further addition is dz by ds equal to 0, and again we look for the Hessian determinant, and then we check the kind of optimal solution. Ultimately, whatever cases which we have already discussed here, and in every instances or every instance means all the instances we find the typical structure is like this. We have objective function, and we have a kind of calculus based structure through which you look for the optimal solution, and that too where what we have done actually we highlighted the first order necessary condition and second order sufficient condition. Ultimately, the optimal values and optimal results, and that to values of the decision variable exclusively depends upon the first order necessary condition, and second order sufficient condition is just to support the particular output. That is one way you can one way you can address that. It is a kind of robustness check to support the or to validate the optimality results. So, so we have a different kind of situations. So, depending upon the typical business problem, you can actually apply a particular model, and then look for the optimal solutions, and look for the values of the decision variable through which you can address the business problem more effectively and as per the management requirement. So, with this we will stop here. Thank you very much.